Very good afternoon, all the participants. Good afternoon, sir. Rajnikant, sir. Am I audible?
Yes, sir. Good afternoon, sir. Yes, sir. You are audible.
Thank you very much,
Yes.
sir, for coming.
Yes, sir.
Sir, please start the session.
Shall I start, sir?
Yes, sir.
Yeah. Thank you, sir. Good afternoon, one and all present here. Today I'm going to plan one demo with the existing code. Then after the demo tonight, I will share all the previous as well as today's code with Dr. Ram, sir. You can get it from him for your research purpose. Okay, thank you. 1 minute. Okay, 1 minute, sir. Thank you, everyone, for joining. I request you to confirm, is it possible to see the screen now? Okay, some of you kindly confirm.
Yes.
Yes. Thank you, sir. Thank you very much. Today, the session is joint thresholding and segmentation of brain tumor. So here we are going to discuss how or what is the need of combining a thresholding with segmentation instead of directly going with the segmentation. First, we'll discuss that. Then, in order to demonstrate the outcome, here we are going to use two different images. First, I'm going to demonstrate the simulation using RGB scaled blood cell images in order to confirm its superiority. That is the need for combining thresholding and segmentation. First, we'll discuss with blood cell image. Then after that, we'll have a brain tumor image. Then what are the steps to be implemented if we want to examine brain MRI in order to evaluate the brain tumor. 1 minute, sir. First, let me switch off my AC. The noise is more here. 1 minute, sir. Okay, I'm sorry for the disturbance. 1 minute. Yeah, thank you. So here our presentation is as follows. Okay, first we are going to study the need of thresholding with some appropriate example. Here I have considered Kapoor's approach to demonstrate the outcome because Kapoor's entropy based technique already proved its through our research. Okay, we come to know that Kapoor's thresholding helped us to get a better result for both the RGB scale as well as grayscale images. Hence, here we are going to discuss Kapoor entropy based image enhancement using multi-level thresholding. Okay, so I also will provide some link. Okay, the thresholding, existing thresholding methods which you can easily get from MATLAB Central website. Okay, I have given the links. Okay, if you follow the link, you can download the earlier codes which was developed using Atsu, Kapoor, Salis, etc. Okay, so according to your research, you can choose any one of the approach and you can enhance the image in order to have better diagnosis. So first we'll discuss some brief discussion. This is the slide organization today. So first we'll have some brief discussion regarding how the thresholding, right thresholding method may be selected. for a chosen approach. Okay, it depends on trial and error method. That is, we have to conduct some experiment with ATSU or Kapur or whatever experiment, whatever method we have. Then we have to choose a best thresholding methodology by making some evaluation, comparison. That is, we have to compare the thresholded outcome with the original image. Then we have to find some performance measures. Okay, that code also available in MATLAB Central. I will let you know what are the code which is to be considered. Okay, to confirm the performance of thresholding outcome. Okay, so if we take a threshold, we have only two choices, possibly ATSU. ATSU is called as a between class variance. Then next is entropy. Under entropy, we have a lot of sub classifications like Kapur, Salis, Fuzzy, then Shannon, etc. Then Rennie also, Rennie entropy. Recently, you can search. If you search, you can find a lot of work which was already published in IEEE transactions. Okay, you can find. So that is the choice of the entropy must be done based on a trial and error or with your previous prior knowledge. Okay, in your earlier research, if you came across some entropy based enhancement, then if you find that the entropy which you already have provides better result, then we can choose that particular entropy. So in order to demonstrate the performance of the thresholding scheme, here we are going to discuss we are going to see the demonstration on RGB scaled blood cell images. That is, it's nothing but a leukocyte image data set which is existing in internet, LISC. Okay, I provided the link. Okay, if anybody, totally we have 5 classes of leukocyte, basophil, neutrophil, etc. Okay, every image is associated. Okay, they already provided image. They already provided the ground truth also. The only thing is we have to develop some algorithm which can extract the leukocyte from the image frame. Then after that, we have to compare the extracted thing with the ground truth. Then we have to make some we have to compute some performance values. Then according to the attained value, we have to confirm the performance of the proposed system. Okay, in literature, we have a lot of methodologies to evaluate leukocyte. Okay, even we can find a methodology called circle detection. Okay, circle detection, because we know that the blood cells will be in the form of circle. Okay, it will be stained. Stained means they will add some coloring agent in order to separate, in order to not separate, in order to enhance this section, the section to be evaluated with the background. Then if it is enhanced using some color which can be easily extracted with a chosen automated or semi-automated segmentation approach. The simplest procedure is circle detection. Okay, circle detection. If anybody is working in particularly the circle detection, okay, yeah, I may share the code. But compared to circle detection, my request is just if you can follow combination of thresholding and segmentation. Okay, it's a unique procedure. It will not suitable only for blood cell. You can use same procedure for any medical images, irrespective of its complexity. Okay, even though it may be a simple image or it may be a complex image, but it must be a 2D image. Okay, two-dimensional image. Either it may be RGB or grayscale. We can implement. So our aim must be, we must develop some system that must work for any image of a chosen size. For example, say if we selected 256 cross 256 image frame, even it is RGB or it is grayscale, the developed algorithm must work. We cannot confirm that this algorithm works well on MRI or this works on well on CT, etc. For the considered data set, it worked well. Then if you want to further, if you want to justify your eminence of the developed system, then along with MRI, we can also use some other complex images. Hence, in order to demonstrate the performance of this joint thresholding and segmentation for complex image, here we considered blood cell images for some demonstration. Then after that, once again, as usual, we have considered a brain MRI slice along with skull section. Okay, here we have considered brain MRI along with the skull section. Then we have implemented a lot of procedures in order to extract the tumor section which is existing in the slice automatically using the watershed algorithm which we already discussed. Okay, so now I have fixed the watershed code. It provides the segmentation accuracy which is greater than 95%. Here I don't have sufficient internet facility, so after reaching home I will share all the information along with the data set to Dr. Ramsar. You can get it from him. The next, after thresholding, okay, thresholding to enhance, I will show with some demo. I will show the outcome, how, what is meant by enhancement, and how the thresholding help us to enhance the particular section by dilating other region. Okay, we'll discuss all these things. The next, segmentation. After enhancing some image, okay, our aim is we have to extract a particular section from the brain image, from the medical image for further assessment. Okay, if we want to extract a particular section, then we have our own choice. Either we can go with semi-automatic approach. Semi-automatic approach, for every image, we have to initialize the task. Okay, either it may be region growing, seed region growing, level set, active contour, Chan-Weiss, whatever it may be. We are going to initialize the process. In seed region growing, we are going to put our cursor and we have to make a dot there over there so that the dot will expand when iteration increases. Otherwise, for level set or active contour or Chan-Weiss, we are going to fix a bounding box over the region. Okay, either the bounding box will converge. If we use the outer box, it will converge towards the region which is to be extracted. If we use inner box, it will expand. Okay, it's called flexible contour adjustment. Okay, this process will be done according to the iteration. Okay, so here another one drawback is, first drawback in semi-automated, we are going to initialize the process. Second is the accuracy of attained outcome depends on its iteration. That is, iteration means sometimes it may take more time to identify all the pixels which is having the trace of the disease. Okay, that is one major drawback in semi-automatic technique. But the main advantage is, okay, even the image is very complex. If we want to extract a particular section, then we can achieve it with a semi-automated approach. But in automatic approach, if it is the image, whole image slice is having some disease-infected section or background or some other section, if all are easily separable, then we can go with automatic technique. Along with watershed MRF, we can also use clustering-based procedures. In most of the cases, the clustering-based procedures may not work when we have grayscale image in most of the cases, because the clustering approach will try to group the pixels. After grouping the pixel, it will separate. So here already in our earlier discussion, we have discussed that MRF uses a clustering technique as a backbone. So instead of using directly K-means or C-means, we can use a MRF based technique which will help us to separate the given image frame into various sections. Okay, then along with these two things, we are going to see just to overview. Okay, what is meant by CN based segmentation? Here you can get code both in MATLAB as well as Python. Not I will not share because the code is already tuned for some data set. If we want to use some other data set, it must be adjusted. Okay, if I give code also, it will not be useful for you for your work. Okay, so I will explain what are the things to be done when we have to implement when we are implementing CNN based segmentation. Okay, if we search the internet, we can find the code in both Python as well as MATLAB for basic unit and segnet. Okay, but basic unit and segnet was developed before around 7 to 8 years. But nowadays they modified the performance of unit and segnet with VGG based techniques as well as ResNet techniques. Okay, in MATLAB Central, we can find the code, working code for both VGG unit, ResNet, etc. Okay, my request is instead of segnet or both work same. Okay, every approach aims to get best result, but here only thing is the time constraints. Okay, if we implement CNN, the time requirement is more than the traditional thresholding, the combined thresholding and segmentation technique. If number of images to be examined is less, then we can go with the traditional approach. When more data, more than 500 or more than 1000 images is to be extracted at a time, then we can go with CNN based approaches. Okay, sir, my voice is audible, sir. Sir, some of you please confirm. Sorry, ma'am. Please confirm my voice, sir. Yeah, thank you. Thank you very much. Thank you. Thank you. So here in joint thresholding and segmentation, first we are going to take our image slice. So it must be a 2D slice. Either it may be RGB scale or grayscale. So first we are taking a 2D slice. Then we are going to enhancing. We are going to improving the disease infected section using a chosen threshold methodology. Then after that, the enhanced image will be fed into some other section where we can segment the infected region. Okay, the disease infected section can be extracted according to based on the semi-automated or automated technique. Okay, it depends on us. Then after that, we are going to compare the extracted outcome with the ground truth. Then after the comparison, we'll come to get some or we'll compute some basic parameters like accuracy, Jaccard, dice, etc. Then based on that value, we can confirm the performance. So as we discussed earlier, in this kind of procedure, that is joint segmentation and thresholding, the first task can be used to enhance the disease section. We are not interested in background or other normal section in the image. We are interested only in disease section. Our aim is the infected section must be enhanced. Then segmentation must be implemented to extract the section. Okay. So here already we have discussed, we can choose any one approach according to the need. Okay, according to the need or based on the expertise or based on a trial and error approach. For example, say we have some image, we have all the codes. Say first I'm starting with Atsu. If I get best result with Atsu, then I can stop with that. Otherwise, instead of Atsu, if I go with Kapoor, so that is we have to do initially some comparison. Then visually, we have to check the outcome. Then after checking the outcome visually, then we have to compute some performance measures. That is, thresholded image must be compared with our original image. During that comparison, we have to take care of the PSNR. Okay, the PSNR, SSIM, then RMSC, then NAE, normalized absolute error. Okay, I will give all the codes after reaching home. Then if the slide I have shared with sir, okay, if you want, you can download the methodologies. Okay, this is the methodology. Just now I searched and yesterday night and I have found. Okay, in MATLAB Central, we have lot of threshold thresholding approaches using heuristic algorithms. Okay, even PSO and its variants like Darwinian PSO, fractional order Darwinian PSO, etc. For OTSU, it is available. Okay, the next if we take some other search, then it helped us to get Shannon-based thresholding with differential evaluation, fuzzy-based thresholding with differential evaluation, and Kapoor-based thresholding as well as OTSU thresholding with harmonious search algorithm. Then cuckoo search also, some she implemented to achieve OTSU's thresholding, Kapoor's thresholding, and Solis thresholding. Okay, so here, not necessary to use all the technique for our task. Say our aim is we have some data set. Okay, the data set was already done by evaluated by someone else. They have demonstrated some result as numbers, say accuracy greater than 90% or 95%, something they have given for the data set. Say if we are taking the data set, here not necessary to show some accuracy which is better than them. That is one other thing. Then we have to evaluate the complexity which is existing in the earlier work. Okay, in earlier work, they have done some complex procedures. Say they got 98% accuracy, average accuracy to evaluate the particular data set. Okay, our aim is not crossing 98.90 or 99, getting 99. It's not our choice. Our choice is first we have to look into the earlier work. We have to identify the complexity existing in earlier work. After identifying the complexity, we should suggest some procedure which can get us some better result. It's not necessary to cross the 98 which already reported. Okay, because already we discussed that we are going to provide some solution to doctor. Okay, we are going to assist the doctor while taking the decision, or we are going to guide the doctor to evaluate the data set as fast as possible. So fastness is major thing. Because if we say our algorithm gives 100% accuracy, we can use it instead of doctor, not applicable. Because at the end of the day, some human or some patient who is a human, okay, who is going to be treated according to the result which we provide. Okay, the result which we provide directly will not be considered to treat the patient. The result which we provide, that is the software-based result which we deliver, will be verified, once again verified by some clinician or by some doctor. Then they will have their own opinion. Then according to their opinion only, the treatment will be implemented. So here it's not necessary to cross the accuracy which something already reported in the literature. Okay, even though we take same data set, we can claim that it will be some other different approach. Someone they done this approach and doing this compared to the earlier work, my work is simple. That is more than sufficient. For example, say we got only 91, but in earlier work they got 98. Their runtime is say 3 minutes. Our runtime is say few seconds. Then we can claim our runtime is lesser, even though the accuracy which we get is less. Okay, our runtime is very less compared to earlier work. Like that, we can justify. It's not necessary because when we do some work, will come to know that already this was this much and we got this much, we got this much. It's not the right way because already someone is having 98. It's not necessary to put some algorithm, develop some algorithm which can provide 98.001. It's not necessary. But we can give our own idea which can minimize the complexity which is existing in earlier work, which can minimize the time which is existing in earlier work. Okay, like that. In that way, we have to work. Okay, thank you. Here, this if you visit these links where you can find multi-level thresholding procedure using ARTSU. It's earlier existing one. Okay, ARTSU, Kapoor, then Salis, etc. Okay, Shannon also there. Okay, you can take the code that from there. Either you can use the code as it is to enhance the medical image which you are considering. That is one thing. Otherwise, already some algorithm will be existing there. Okay, for example, say someone is using PSO. PSO is a widely approved or accepted heuristic search. Say we are going to improve the PSO, which can provide a best result with minimal time. Okay, like that. In that way, we can. It's not necessary to. It's not necessary to modify the PSO. We can use the PSO as it is. Then we can adjust or tune some other values, which can provide faster convergence. You can. Otherwise, you take the code as it is. You execute it for your data set. You'll get some result. Then from the result, you try to infer something and you convert that thing as a paper. That's more than sufficient. It's not necessary to modify the thing, nothing. Just whatever you get. Otherwise, you tune some other parameter in the algorithm. Then you try to get some result and you project in that way. Okay. Okay, already we have discussed this sufficiently. Yes. Okay, this is the demonstration. Today I'm planning to show. I have checked the code is working and we are getting more than 95 plus accuracy. Say this is the brain tumor image which we collected from TCIA LGG, low grade glioma. Okay, TCIA is a cancer imaging archive. Okay, you can find, otherwise simply if you can type this, you can see a website. From the website, first we have to download a software. Okay, some information will be provided there. First we have to download software. Then after downloading the software, then we have to go to then we have to download the link. It is like a DICOM file. DICOM file, we have to download the link. Then after that, the link must be opened from the software. Then if we run, it will extract all the patient's images in a folder, patient 1, patient 2, like that. It will give the outcome. For every patient, we will be having different modalities like flare, T1, T1C, like that. Okay, TCIA, why TCIA is widely adopted as TCIA gives the real patient data set. Real patient means some patient who already diagnosed with some brain tumor in some country. Okay, for research purpose, they will donate that image in some dedicated location. That location is the TCIA. Okay, otherwise, if you are getting Similarly, along with LGG, we will be having GBM, glioblastoma. We have that thing also. Otherwise, if you get any difficulty in downloading the particular data, you please kindly let me know so that I can help you. Okay. Then say here we have extracted. Actually, it's a 3D image. 3D to 2D conversion initially necessary. It can be done using any approach, particularly ITK snap. Say with the help of ITK snap, say we have extracted. Sorry. 1 minute, sir. 1 minute. Sorry. Yes. I hope you can see it. So here we have extracted, sorry. Here we have extracted the 2D slice initially. Say this is the 2D slice. If here our major aim is we have to extract this tumor section. Okay, this tumor must be extracted accurately. Then if we use automated approach, okay, otherwise if we see the threshold level of the tumor as well as skull, both look similar because the skull is also bright, having bright pixels. The tumor is also having bright pixels. So here we should use some procedure that's called skull tripping methodology, which must eliminate the skull. Okay, it's an algorithm. It's a we have to set some threshold. Okay, it's a bi-level thresholding like thing. If we set some threshold, the given image will be separated into two sections. Okay, with one image will be the skull, approximately the skull. Another image will be the normal tissue without skull. Okay, so if if we implement skull stripping, then skull will be removed, then we will get this kind of image. Then if we take TCIA data set, TCIA, LGG or GBM, both will not provide us the ground truth. But we have to confirm that our approach is giving best result. Hence, we have to develop the ground truth if possible. Otherwise, if we feed the algorithm with ITK snap and there is some adjustment there, that will help us to extract the tumor. The extracted tumor, which is in binary form, this one, okay, can be considered as this green. Sorry. This can be considered as the ground truth. Then after skull stripping, say here we are implementing a heuristic algorithm based thresholding. Okay, here the threshold value can be selected like 2, 3, 4. Only 2, 3, 4 alone sufficient. Okay, after implementing bi-level thresholding, we have to check the outcome of image. If it is okay, then we can stop. Otherwise, we can ignore bi-level thresholding. We have to try for 3. Otherwise, if it's not providing output, then we have to try for 4. Okay, we have to do this initially only once. Because if we fix the value level once, then same threshold will be implemented for other approaches. For example, say this is the thresholded outcome, say it is a Kapoor's thresholding. Then after extracting the particular, sorry, after enhancing the particular tumor, here we can see this is our input image. When this the input image is passed through the thresholding operation, here we can see the normal brain section will be dilated. Dilated means it's not removed, it is hidden. Okay, it's a dilated and its value will be approximately similar to the background. Here you can check. Okay, the normal brain section is dilated and it will look like the background. But if we see the tumor section, this tumor section is clearly visible to us. So this tumor section can be extracted using any segmentation procedure. Either I can go with semi-automated procedure or I can go with automated procedure. But here, if we have the aim to reduce the time of the diagnosis, then we have to choose automated technique. A simplest approach is watershed segmentation. Okay, watershed combined with some thresholding help us to provide best result for any data set. Either it may be a grayscale or it may be RGB scale. So if we take a watershed algorithm, it provides a lot of intermediate results, but we are interested only in the tumor section. After extracting the tumor section, we must we must do some comparative assessment between the ground truth as well as the extracted tumor. Okay, pixel level. Okay, pixel wise we have to compare. That is, if you take the tumor section, if we consider the tumor section, say the white region is called as true positive. Okay, the background black region is called as true negative. When we compare this and this, if during the comparison, if white of ground truth lies at black of the actual segmented image, okay, if white is identified as black, false positive. If black is identified as white, it's a false negative. That's all. Okay, true positive, true negative represents the tumor. Tumor is true positive pixel. The background, the black color will be true negative. Okay, if during comparison, if there is any mismatch, then it can be identified. That is, if white is identified as black, then 1A, that is false positive. If black is identified as white, then it is false negative. Okay, so based on the TP, TN, FP, FN, we have some formula. With that formula, we can compute the other measures like that's like in confusion matrix. Okay, true positive, true negative. Sorry, with the help of this, we can compute accuracy, sensitivities, precision, specificity, F1 score, as well as negative predictive value. Okay, if these values are greater than 90 or 95, then we can confirm that the proposed methodology help us to get appropriate result. So here, as we discussed here, first I'm going to show a small demonstration with the blood cell image so that we'll come to know how this this procedure works for RGB scale image. So here we are going to discuss with the LISC dataset. The LIC dataset consists 5 different blood cell image, particularly leukocyte, okay, or white blood cell. It will have 5 different white blood cell. Okay, along with the white blood cell, it has this dataset also consists ground truth. Okay, ground truth. So we can download the image there if we are interested in doing some research work. Say this is a sample image from the dataset basophil. Say the background section. Here we can see something. Say the background section shows normal cells. Okay, this is the leukocyte section which was stained or colored with some coloring agent. Okay, after preparing the slide, they will add some color in order to separate the section that is the region which is to be examined with the other section. So here the major drawback is if we use ordinary segmentation, it is not possible to separate this section with the background. Okay, in some cases, in this image, it is clearly visible. In some cases, say here they are adding some color instead of this, then the colored section will be very tiny compared to other normal blood cells. Okay, if this is the case, then we will get some problem when we implement a conventional technique. Say if we combine thresholding plus segmentation, then we can easily achieve best result uh, due to the enhanced disease section. For example, say here we consider Kapoor's thresholding in order to enhance the test image. Okay. Say in Kapoor's thresholding, first we have implemented bi-level thresholding, then 3-level thresholding and 4-level thresholding. Here we can see when we implement either bi-level or 3-level or 4-level, here we can check this thresholding dilates, it's not removes, dilates or reduces the visibility, reducing the visibility of background compared to the section which is to be examined. Say in bi-level thresholding also, we can easily find where our stained content is there. Okay. In 3-level also, we can find where we have that particular thing. In 4-level also, we can find easily. Because if you take the background is dilated. It's not completely removed. It's dilated. If we want to completely remove the background, then we have to apply segmentation. Okay, when we implement segmentation, we can extract only the stained section, then background will be say if it is a binary image, the stained section will be pure white and background will be dark, that is black. Okay, so thresholding can be used to dilate the background and enhance the section to be examined. So here this is bi-level. Okay, the choice of the level only depends on us. Okay, we cannot say this gives best result, this gives best result. Here our aim is we have to develop a system which can produce us the result as early as possible. That is, time must be reduced. Okay, the next here either we can select bi-level or 1 minute, sir. Here we can select bi-level, tri-level or 4-level. Okay, based on visualization. If visually, if we check here, we can say 4-level provides clear background compared to level 3 and level 2. Okay, visually, if we check the background in level 4, that is threshold, 4-level threshold. Multi-level thresholding, if you see, thresholding level value may be selected like 2, 3, 4, 5. In olden days, nowadays they are considering in steps of 10 or in steps of 5. Okay, so that's beyond our scope. Here, if we see the image, say initially we have a 2-level, 3-level, 4-level. The background section in 4-level is very clear compared to 3 and 2. But the time taken for the 4-level thresholding is very high compared to 3 as well as 2. So the choice must be done done by us according to the experience or our own choice. Otherwise, technically, if we want to do the choice between 2, 3, 4 levels, we have to compare the thresholded image with the original image. We have to make some comparison, pixel level. First pixel and this first pixel, like that, pixel level comparison must be done. Then we have to compute the performance measures such as normalized absolute error, root mean square error, PSNR, FSIM, okay, NCC, normalized cross correlation. Okay, this is structural index. Okay, similarity index, structural content, mean SSIM, the mean structural similarity index. So when we compute mean structural similarity index, okay, it will compare the first image and second image. Whatever section matches perfectly between first image and second image, that will be enhanced. So if we take that SSIM mapping, okay, actually SSIM is a separate code. If you run that code, it will also give some value in the form of a matrix. Okay, if you plot the matrix, then it will give an image like this. Say this is your original image, this is thresholded image. If we perform pixel-wise combination of first image and second image, we can get the similarity, the structural similarity between this section and this section. This is a grayscale. Here, if we check here in this image, we can see these two sections are having perfect match. Okay, this section in original image and this section in threshold image are having perfect match. Then when we compare these two, here if you take individually, we cannot see clearly. If you compare these two, here we can check the particular information. So this is gray level. Similarly, we have a lot of color map like hot color map, etc. Say this is Parula color map. Okay, in MATLAB, you can check the color map, then you will try to find a lot of HSV, etc., etc. Okay, so gray, if we cannot see the thing clearly, then we can go with some other images. Okay, it's a complex image. The image complexity is more, hence it looks like this. If we take a brain image and it will be very clear. The structural similarity will be very clear than this. Here, this is complexity. Complexity of this LASE images more, leukocyte images more. Hence, the similarity is not appropriate. It's not visible clearly. Similarly, if we take a Parula color map, it may look like this. Same image, we are changing the color map. Here we can find the blood cell. Okay, just it's some demonstration. Okay, here if we are not interested in color map, we can stop only with this. We can compute the mean structural similarity index, then we can stop. We can ignore this particular thing. Okay, in some research work, they have given the image. If they are comparing image, they're also providing the structural information about the image. If we take that image, either it can be represented in grayscale or it can be represented in other color map. Okay, so this is to demonstrate. Okay, this is beyond our topic, but this is to demonstrate how the thresholding help us to enhance the section. Okay, enhance the region which is to be evaluated. Okay, so here if we take this particular image, it is very complex image. Okay, complex image. In some cases, the stained, that is the colored section will be very small. Okay, if we have that kind of image, then if we implement a multi-level thresholding, then it will help us to enhance the section. Then after enhancing the section, either we can select a particular threshold 2, 3, or 4 for our implementation based on our visual outcome, visual verification, or some mathematical verification. Okay, this is mathematically we are computing some values for bi-level, tri-level, and 4-level. If some value is best in some method, then we can choose that particular technique for implementation. Okay, so this is regarding RGB scale image. This is optional. This one is optional. That is this SSIM is optional, but we have to compute SSIM value. Okay, so this is widely necessary when our task is only implementing thresholding. Okay, if we are our research is only implementing thresholding for some image, these measures must be computed. Okay, the code which you already it's existing in MATLAB. Only thing is every code is available. Just we have to take it, we have to explore it, then we have to combine one code with another code in order to have a complete software. Okay, that thing you can achieve only with experience. Experience means, say, day by day, if you are taking some code, you are continuously exploring the code for a few days, then you will come to know what are the things available in the code and what is missing, what to be added. Okay, this is a chain reaction like thing. So continuously, if you are adding some enhancement in your earlier code, then after few days or few months, you will have a complete code which can work for any image, any medical image, either it may be RGB or it may be grayscale. So you please kindly remember, sir and ma'am, whatever code we develop, that must be unique. Unique means it is not dedicated for RGB. It's not dedicated for grayscale. It's not for MRI or it's not for CT. The code is a code which must work for any image image of a finite size. Say, for example, 256 cross 256 MRI, we have developed some code. It must work for our CT. It must work for some blood cell images, skin cancer images, etc. But the code which we develop here will not work for X-ray, because X-ray the visibility will not be clear. Visibility of the infected section will not be clear. So we cannot use the particular code to evaluate X-ray image. Okay. The next, let us discuss about skull stripping. So what is the need of skull stripping? So just now in our that block diagram, we have discussed about skull stripping. So if we take it's nothing but filtering, okay, removing some unwanted sections from an image. For example, say we have a group photo. From the group photo, we need only a particular person to be examined. Then we can cut and take that particular person in some other location. We can enlarge him and we can analyze. Okay, so removing or eliminating other persons from the group photo is called as artifact removal. Artifact means some unwanted thing which is associated in the particular image. Okay, so this can be achieved with filters. Okay, filter, particularly thresholding filter. Okay, if we implement the same technique for brain MRI with a skull section, then it is called as skull stripping procedure or skull elimination procedure. So for example, say we have some CT data, lung CT, either COVID-19 or normal lung CT data. Here, we know that only these sections are lungs. Okay, if we have COVID-19 infection, we'll have the infection only at this location. Similarly, if we have a pneumonia, it also will be at this section. Okay, here, other sections. So if we take this image, this section is an unwanted thing. Then this section is an unwanted thing. This section is the heart. Okay. Our aim is we are going to develop some methodology to examine the lung region. Okay. Lung region, whether it's normal or having some pneumonia or having some other infection, viral infection, or it is having COVID-19 infection or not. Say that is the task. Okay. Here manually we can do. Manually we can cut this lung alone. Okay, manually we can have a trace in some software. The software will cut the lung according to our need. That is the first thing which can be done. If number of images, say 10 or 20, manually we can cut and manually we can remove every lungs. But say it's a COVID-19 hospital, say they are taking lung CT, say the patient size is more than 500 or 1000 per year, per day, then the number of slices per patient is say 200 or 10, 100. 1000 patient into 100 images per patient. The image data set is huge. For huge data set, manually we cannot cut the lung section. But our aim is we have to examine only the lung section. So during that condition, what we are going to do is we are going to implement some filter. Okay, thresholding filter, just a color filter, which will separate this gray, light gray, sorry, dark gray. This is light gray. Okay, which will remove or uh, separate this section with lung section. So if we remove this, okay, if it is a feature extraction task, if we remove this, then we can minimize the complexity of image section which is to be examined. But if it is a normal image, if we give this as it is, background it will ignore because the background is assigned with a value, threshold value 0. But other sections, the algorithm will examine this part, it will examine the lung section, it will examine the white sections. Okay, but if we remove this section, this examination can be minimized. So wherever we have this section is now replaced with black. That means the algorithm simply ignores the section and it will examines only the outer section as well as lung section. So we can say the complexity in image is reduced. So the algorithm's examination time can also be reduced. Okay, so this filter, this is called artifact removal procedure. If we implement this filter, which will remove the art and other sections from the CT. Similarly, if we implement same thing, here we can see some regions are missing, no issue. But instead of having the whole thing, here the whole white, this white region can be easily extracted if we use a skull stripping procedure. Okay, otherwise if we want to implement only a manual approach means say I'm going to implement a bounding box. The bounding box will shrink according to the iteration. Then it will extract, after shrinking, say it extracts the brain section, tumor section alone. Then no need to follow skull stripping. So we are going to decide whether we are going to implement the skull stripping or not. Our ultimate aim is we should get some appropriate accuracy. Okay. Also, the runtime of the whole algorithm must be less. That is, with minimal time, we have to get best result. So in order to get best result with minimal time, we have to include all the possible procedure which help us to get best result. Okay, so this is regarding the skull stripping. So if we are interested only in semi-automated segmentation like level set, etc., then we can stop with, we can ignore skull stripping section. Say in our work, we have implemented automated segmentation using watershed. So here we have implemented skull stripping. The skull will be removed. Then after removing the skull, we have implemented Kapoor's thresholding, okay, with level. Threshold level is equal to 2. The Kapoor's thresholding converted this section into a background and a clearly visible tumor section. The clearly visible tumor section is then extracted using watershed algorithm. This is the extracted watershed. This is the ground truth of this image created using ITK snap. Okay, like yesterday we discussed, not yesterday, Monday we discussed, if we use manual segmentation, then we can trace the regions. Okay, this region also will give us the approximate ground truth. Okay, this is the ground truth which was developed using ITK snap. This is the ground truth which we just assume, which otherwise we can clearly also we can extract. Slowly we have to draw or trace the pixels if we use manual segmentation. So this is the approximated manual segmentation. This segmented outcome must be compared with the result which was attained, the result which we get from watershed. Okay, so after getting this result, once again we have to do the comparison between white section and white section and black section and black section. White section true positive, black section true negative. During comparison, say the white region which is identified as black will be white region identified black as false positive, black region identified as white is false negative. So with these values, we can compute the measures like, here you can check true positive rate, true negative rate, false positive and false negative. Always the things like true positive and true negative must be more compared to false positive and false negative. Then here, why we kept both together is, here if you compare, 1 minute sir, if we compare true positive with the sensitivity, both look similar. That is true positive rate and sensitivity both are same. So here in percentage, if we take 87.7, formula and all you can find easily in confusion matrix. Okay, in a wiki, in Google confusion matrix, comma wiki, like that if we type, okay, there it will give a page there we can get all the formula, okay, all the measures which is widely adopted in data science, okay, where you can find the formula or confusion matrix procedure for bi-level as well as multi-level classification. Similarly, there you can find the formula for Jacquard dice. Every formula is available in that particular location. Confusion matrix, then wiki. Then if we take a true negative rate, here just like that we can compare. Okay, true positive sensitivity, true negative specificity. The next F1 score is nothing but dice coefficient. Okay, sometimes if we are not interested in F1 score, then we can use negative predictive value as our outcome. So if we compare these two, that is segmented outcome and the ground truth, we may get these values when we get best values of Jacquard dice accuracy. This alone sufficient to confirm the performance of the system. Okay, so after confirming the performance, then we can compare the attained outcome with some other outcome result which is already existing in the literature. Even though our accuracy or Jacquard or dice is lesser than the earlier work, then we can justify or we can justify our performance, the performance of the proposed work, by having a comparative analysis between earlier approach complexity, the complexity in earlier approach and the easiness of the proposed technique. Okay, then if you done sufficient things with the traditional technique, Then if you find that you want to do more, then we can choose CNN based segmentation techniques. Okay, in CNN based segmentation technique, instead of having the existing instead of developing our own traditional own customary approach. 1 minute, sir. Sorry. Instead of having our own customary methodology, say we have to build some methodology from the scratch, it's time consuming. So instead of building the own thing, we can use the existing thing in the literature. Existing thing means we have only two basic things in a CN segmentation. One is UNet, U-shaped convolutional neural network. Then next one is Segnet. Okay, the sufficient codes, basic codes, either in Python and MATLAB is available. Okay, I can share it with you later. Okay, if you are not interested in using the conventional code, and if we are interested in advanced one, then instead of having a simple unit and segnet, we can go with BGG supported unit as well as segnet. So in in the literature, they have given, that is in website, they have given VGG, okay, 12, VGG 12 based layers, that is VGG 12 supported unit and VGG 12 supported segnet. Okay, instead of using the VGG 12 based unit as well as segnet, we can simply replace the existing VGG 12 unit with VGG 16. It is easy. So just we can take some developed VGG 16 architecture as it is. Then we can have that architecture as our encoder section, which converts image into features. Okay, up to this it's encoded, this part. Then after that, from the feature, we have to do grouping of pixels. From the feature, we have to rebuild the image with the grouped pixels. Then finally, we can have a softmax, okay, which can help us to separate the pixel with the best intensity with the remaining thing. That is, we can have a binary separation. Then it will separate the tumor section from background. Other regions will be considered as background, and the tumor can be considered as the region of interest. Okay, this thing, it's the VGG 16 based unit also existing in internet. This is unit. 1 minute, sir. Sorry. So this is the architecture of Segnet. So working wise, both are approximately similar. The first section is the encoder section. Here, only thing is according to the methodology, both will differ. That is the implementation procedure. Construction and working wise, approximately both are similar. This is the unit and this is the segment. Both help us to get some segmented output when it is properly tuned. Okay, so in order to make the system to learn and segment the particular image section, so it is our duty to train the particular network using sample images. Okay, if it is a VGG based technique, then we must use our image dimension as 224 cross 224. Same network can work for both RGB scale as well as grayscale images. But if we go with a conventional conventional unit or a conventional segment, according to the pre-trained model which we are going to use, the size of the image will vary. That is, in some VGG may in some unit, sorry, VG not VGG, in some unit they may give actual image as it is, that is, which is greater than 224 cross 224. So here the thing which must be remembered is, first we should aim to develop some procedure which must be suitable for any image. Okay, here for example, say if we are developing some procedure for blood cell, we must use same image for skin cancer. Okay, if we use same image for skin cancer, we can ignore this procedure. That is skull stripping or artifact removal. Skin cancer not necessary. Directly we can give the skin cancer test image to multi-level. We can we can execute the thresholding on the test image. Then we will get thresholded output, okay, for 2 3 4 based on our choice. Then the thresholded output will have an enhanced section which is to be extracted. Then after that, we can implement a chosen segmentation procedure to extract that section. After the extraction, this extracted region must be compared with a ground truth. Okay, after the comparison, we'll get some performance measure. Then the performance measure must be recorded as a table. Then based on the value, recorded value, we have to justify the proposed approach, help us to get this much of accuracy with this much of time. Okay, so this is a simple technique which consists only two major work or task. One is thresholding and segmentation. Like that we can conclude. Now, if you permit, then I can show some demonstration with the software, MATLAB code for skull stripping, then thresholding, okay, then watershed segmentation. Watershed segmentation already we have discussed. So first, let us discuss about skull stripping first, then thresholding for RGB scaled images. Okay, here I have considered only LISC because it's one of the complex image. Extracting the particular section from the image may be difficult. Okay, if we use clustering technique, it is possible, but we cannot rely only on the clustering technique because the clustering technique may work on some images which may fail to get thresholding. Okay, you collect some images. Okay, if image is necessary, few images, say 100 images, I can share because here due to some bandwidth issue in my mobile, in home I cannot share. Okay, otherwise I will help you to provide the link from where you can take MRI. Okay, MRI not only for tumor, we have stroke data set. Okay, then we have multiple sclerosis. Okay, this is another one disease data set, but the MS segmentation, multiple sclerosis segmentation from MRI is one of the challenging tasks which we can easily achieve with the proposed technique because we have developed some methodology. We are getting some good results, say 90 plus accuracy when it is MS data set. Okay, but if we try same segmentation with unit, that is VGG unit, we are getting good accuracy, that is 95 plus. But getting 95 plus using CNN is okay, but the CNN's training time is more than the traditional approach. So 90% result alone sufficient. Like that we have concluded. So the data set location I can share you. Okay, you can, if you are interested, you can, but initially you try to start, in order to learn the task, you start with the image whose complexity is less. That is, the abnormal section must be visible to our eye easily. Then after that, we can implement any procedure. Then we can get the outcome. Then after that, we can make some comparison. Then we can confirm this work is best, and it can be used for some other data set too. Like that, we can conclude. So I request your permission to make some demo for skull stripping first. Then after skull stripping, then we'll have some demo for multi-level thresholding of RGB image as well as grayscale image. We kindly, kindly, sir, voice it's not clear, sir. Sorry, sir. Just now only I saw your chat. Sir, now is it okay, sir? Yeah. Thank you, sir. Thank you. Thank you very much, sir. So now let me share. Let me demonstrate skull stripping first. Then after that, one minute, sir. One minute, sir. I hope you can see this. This is the skull stripping algorithm. So here we have to fix, because we know that the number of threshold. First, what we have to do is, first initially we have to fix it for one image, because we know that if some patient, for example, say he is scanned by some scan center, say is having a flare modality, mostly the intensity of the image which is coming out, irrespective of the gadolinium or whatever it may be. So the intensity of the particular flare image which we are getting from the particular MRI machine, say it is same. Like that we have to assume. So initially what we have to do is we have to do some threshold. We have to plot the threshold of the brain slice. Then from the threshold, we have to uh, make some initial trial and error assessment till we can identify some threshold which help us to separate the given image into skull and without skull. That is an image without skull. Okay, so it must remove the skull section from the actual image. So it is a manual tuning. Okay, by trial and error method, manually we have to tune. So in order to tune this, we are going to use a threshold value. Threshold we are going to set. So if image value is greater than, that is what say we are initially getting the image, then we are going to keep some image part whose thresholding is greater than some value. Then we are going to remove some other section whose threshold is lesser than this. Like that, we can make some comparison. Then, so here, I hope you cannot see it. Sir, is it possible to see the folder now? Sir? This folder, is it possible to view? No. 1 minute, sir. So this is the folder which we consider to for demonstration. The ground truth, it's already I hope you can see it. The ground truth, it was extracted for demonstration. I have considered only one image. So the ground truth we have developed using ITK snap. Say this is the test image which was obtained from TCIA. Okay, cancer imaging RQ. Then here, say we are applying threshold filter now. Okay, this is a skull stripping algorithm. So we are implementing it now. Here we can see after stripping the skull stripped, that is the skull removed image can reach here. Okay. 1 minute, sir. I think it was saved somewhere else. 1 minute, sir. Yes. One minute, sir. Yes. So when we run the particular algorithm, okay, this is actually it should we can ignore it. So this is our input image. This is our skull stripped image. Is it visible to you, sir? So some of you please confirm, is it visible? Are you able to see the skull stripped image now?
Yes, sir.
Yes, thank you, sir. So if, for example, say we are deleting this, then if we run the algorithm, okay, using that threshold filter, but initially we have to select the filter's threshold value. Okay, so when it is executed, we will get this image will be considered. Say this is our input image. Then after that, it the skull section in this image will be removed. Okay, after removing the skull section, okay, this image, the skull stripped image, is then considered for the other operations like multi-level thresholding, particularly 2-level or 3-level thresholding. Then after that, watershed-based segmentation. Okay. Similarly, here for the next task, say we are going to consider the data set. Either we can consider image 5, I think you can see it, or image 48 for the demonstration of the Kapoor's thresholding task. Okay, 1 minute, sir. Now you can see MATLAB. Yes, say here I already have same image. Say initially I am using bi-level thresholding. Now it's executed. Yes. So this is the outcome. Sir, is it possible to see the result now? Sir, are you able to see the result?
Yes, sir.
Yes, thank you, sir. Thank you. So here, this is the outcome when we implement a bi-level. Here it is 2. Then, for example, say instead of 2, say we are using 3 now. Like that. Okay, like that we have to use various levels. Then we also should compute the time which we take. Okay, the time in the algorithm can be computed. So in the initial line, the TIC tick, then last line TOC, that will give us the simulation time taken by this execution. Okay, so but the simulation time also depends on the processor speed, that also a constraint. So if we want to discuss something based on simulation time, then we can compute it, sir. So for 4 level, say the time taken is more compared to other 2 methods. Yeah. So it's a 4 level. So we can keep on increasing, but we have to stop. That is the thresholding is only to enhance the section. Here our major task is not thresholding. Say here our major task is segmentation. Segmentation means extracting the disease infected region. That is the major task. So here if we are increasing the level, the image quality is not good. This is the output when level is 5. So we can stop either with 2 or 3 according to our choice. Okay. So if we want to, here you can check, sir. 1 minute. Here, if we want to stop, or if we want to choose a particular image for demonstration, so before considering the value as it is, both the image, that is original image as well as thresholded image, must be compared. Okay, it must be compared. Okay, in order to have some measures. Okay, so this measure, like already we discussed, it is used to get the values of the performance of thresholding. Okay, it's used to find the performance or the merit of the implemented thresholding technique. Okay, the first thing we should compute RMSC. Second thing we should compute PSNR in decibel. Third, SSIM, like that. Some measures must be computed according to the measure value. Then we have to choose this is best and this is best, like that. But our aim is only extracting the infected section. We can ignore this kind of comparison because our aim is finally we have to extract the infected region. Thresholding is an initial procedure which can help us to dilate, not remove, dilate, removing the whole other things by keeping the required thing is called a segmentation. Dilating and enhancing this will be thresholding. Okay, so the thresholding is an initial pre-processing approach which dilates the background and it enhances the region which is to be extracted. Then after that we have to implement some other procedure which help us to extract the section. Then after extraction it help us to compute or it help us to make some other comparison to get some values. Based on the values we have to confirm the merit of the proposed scheme. 1 minute, sir. Now let me do the demo of the watershed. I have fixed it. So this is the watershed algorithm. Here just simply I am taking skull stripping image, thresholding and all already I have implemented inside the algorithm. This is level 2. Then here that is in line 4. We have to give the thresholding value, either 2 level, 3 level, 4 level, up to 4 enough. More than 4 it will not give appropriate result. Okay, we can do it by trial and error only for one image. Then after fixing this, Then if you can put 100 images in a folder, here you can call the image like I is equal to 1 to 100. Okay, call this. Then you put it in a loop like I 1, 2, 3. Another, if you put it in loop, then after that, this work will be continuously executed till the loop value becomes 0. Okay, that is, it takes automatically, it takes images from the folder, it executes, it stores the outcome in some location in folder, that is image in some folder, computed value in Excel sheet. Like that, if we can do, then it will be done automatically. But only thing is, initially we have to fix the number of threshold which we are going to use for one image. For one image, if it is done, same work will be executed for remaining images in the data set. For example, sir, if we consider this, say this is our algorithm. For line number 4, we have to set the level. Then we have given the ground truth at 76. Ground truth already we have given at line number 76. Then now we are going to use skull stripped image. Then the skull stripped image will be treated using bi-level thresholding. After that, we are going to implement watershed algorithm. Watershed algorithm extracts the tumor section. After extracting the tumor section, it compares it with the ground truth. After comparing it with the ground truth, it will perform some pixel level comparison, and it finds TP, TN, etc. 1 minute, sir. Let me execute this. Yes. Now you can find, okay, we have executed the task. Okay, it is given all the necessary outcomes. These are intermediate outcome. You can ignore it. Okay, you can ignore these things. Okay. So this is the original image. This is the second one is the edge detection, detected edge. Third is the watershed value. Fourth is the extracted image. This is the ground truth. So if we compare everything, that is, if we compare the extracted image with its ground truth, we are getting these parameters. TP. TP is nothing but white region in the binary image. TN, black region in the binary image. False positive. During comparison, black section identified as white. Okay, false negative. During the comparison, white section identified as black. Then positive pixel, negative pixel. That is positive pixel is that during the combined value of white, combined value of black. Then true positive, true negative rate, etc. Already we discussed. True positive rate is sensitivity, true negative rate is specificity. So here, if we take Jaccard index, it is around 86%, dice coefficient 92, accuracy 99, all are good values. Sensitivity is around 87. So that's all. So if we can do this kind of analysis for one image, then we'll come to know that the algorithm which we developed works well on the particular image. Then we can fix the algorithm unaltered, unchanged. Then we can have similar kind of 100 or 200 image in some folder. We can take all the images one by one. We can evaluate and we can store it in some particular location. That is the image, extracted image in some folder, extracted performance measures in Excel value. Then after that, instead of discussing with the help of single image, we can find the average of accuracy, Jaccard something. then we can say if this approach is implemented, we can get average this much, etc., etc. Either it can be compared with the earlier work, or it can be justified with your own work. Like in earlier work, these are the things they have implemented. This approach seems to be complex when it is implemented. Then this work, the work which we develop, works well on this data. We also tested this on some other data. It also provided the best result. Like that, we can have some comparison. Sir, with this, I stop, sir. I request your um,
Hello.
sir. Yes, sir. Sorry, sir. Can you hear me, sir? So if
Yes, sir.
we have, if any discussion, if you are to do, or if you want to give any suggestion, okay, I request you to unmute your mic and have a discussion with me, sir. So I can provide the data set today after reaching home. I can provide the data set, few images. I can provide all the codes which I have demonstrated here, except CNN, because the CNN which we developed uh, for our system may not work for your system. That is another one drawback, because here we have the particular code in some system which is having sufficient VRAM as well as sufficient RAM. Then this may not work well on the system which you may have, because initially it must be trained. Okay, then after that testing, it takes few minutes, but training, okay, according to the data complexity as well as our softwares, that is systems condition, it varies up from few minutes to few hours. Okay, initial training, but testing is easy. But my kind request, initially, if you want to start some work, you please start with the conventional technique. You explore all the possible conventional techniques which you can, whichever possible. Then after that, the result which you get in conventional technique with some other data, you try to compare this result with your own CNN. But initially, if you start with the CNN, um, developing our own CNN will take more time. That's why still we are, our group, still we are using pre-trained models, because developing the model from scratch is very difficult. Even though we develop the justification, that is justification means publication of our developed work in some reputed journal by comparing it with some existing one will be difficult. That's why it's pre-trained model, no issue. But pre-trained model also requires some more adjustment when it is to be implemented for a particular data. Okay, that's also a task. But initially, if you are starting, my kind request, there are a lot of data sets available in particularly, I think if you have IEEE um, access, IEEE not access, IEEE membership, you can download a recent medical data set from IEEE port. It's a data port. They have a lot of data sets. Okay, IEEE port. Either we can download it from there, or TCIA, that is another one website, or the grand challenges. But in grand challenges, registration is necessary. Okay, when we register, then they have to approve our registration. Then they will give us the link for data set. Okay, normally they will not give the fresh data set. They will try to give the old data, that is their earlier version. So for example, say if they posted something this year, they may give free access to their earlier, that is previous year's data set. Fresh data set they may provide only to the competitors. That is the another one. Another one location is academic torrents. Okay, that is another one location. Okay, where we can without any registration, we can search the data set and we can get the data set. But initial work, if we are doing so, we are starting some initial work, we should prefer the data set which is having the ground truth. Then only we can, that is classification alone not sufficient. We have some bunch of images, just simply segregating it into best and worst, not use. Okay, if it is best and worst, best we ignore, then worst we take. Then here, what is the size of the disease? Where do we have the disease? Like that. If we want to do the analysis, then segmentation is essential. Only classification alone not sufficient when it is implemented in real time. But we should we should remember that getting 95%, 100% accuracy is not a matter. Okay, we have to suggest some procedure, okay, which can provide us some good result, not best result, good result with minimal time. Okay, good result with minimal time is more than sufficient compared to the best result with the maximal time. Okay, we are going to develop some methodology in future which may assist some doctor who involved in some disease examination and decision making process. So okay, with this I stop, sir. I request your interaction. Then we have some, if you have any discussion or if you have any suggestion, I'm ready to accept. Thank you, sir. Thank you very much.
Thank you, sir.
Yes, sir.
Sir, there is one question in chat box.
Yes,
Can you
sir.
suggest data set for MRI?
MRI, magnetic resonance spectroscopy. Sir, I'm not clear. If I can speak with the ma'am, it will be easy. Ma'am, please unmute and let me know
Okay,
your. Yes. Ma'am?
Hello, sir.
Yes, ma'am.
Rajnikant, sir, you have cleared so many doubts of mine, so thank you very much.
No. My request is what kind of data set you are in need, ma'am? Magnetic resonance spectroscopy. It is fluorescein or ordinary?
No, sir, my question is on occlusion sensitivity, sir. How to implement heat map function or line function in MATLAB, sir? Is there, are
Heat
they,
map. Heat map function. No, you want to enhance some particular section. I'm right, ma'am.
yes, sir. So,
Then instead of implementing heat map, there is a code called as saliency detection. Saliency.
okay, sir. Huh.
Okay, if you implement that code,
Okay,
that will enhance the abnormal section. It's like a heat map. That is after enhancement.
okay,
If you plot the image will be in some other color.
okay, huh.
Okay, we have definite some choice for color map like HSV, hot, something.
Okay,
If you choose the right color map, then you can get better visibility of the particular section which you want to examine. That is saliency detection.
yes, sir.
Saliency. The code
Okay,
is
sir.
there. I don't
I have
remember the
noted.
spelling. Yes.
Okay, sir. I have noted.
SALIENCY, I think.
Yes, sir.
Saliency.
Yes, sir.
Yes, ma'am.
Saliency detection. Sir, these
Yes.
occlusion sensitivity and line function are they meant only for particular pre-trained neural networks, sir? Like
No,
Google Net or some. If we use that
no.
function, it's
Google, wait, ma'am. Sorry, our aim is we should implement some CNN,
okay,
okay, which gives some not best result. We don't want always 100% result. 100% result, if we get, that's called overfitted result. Sometimes that may be considered as error.
okay,
Okay.
yes, sir.
So we don't want overfitted result anyway. So we
Okay,
need some acceptable results, say 90 to 95. That is our requirement.
yes, sir.
So if you take a Google Net, ResNet, etc., you try to see the structure, that is number of layers.
Okay,
Number
sir.
of layers which is existing. Just you can compare the number of layers, number of convolution layer, number of max spool layer, then etc. Okay, initially you can compare. There is AlexNet, VGG, like that you can compare. In MATLAB, there is one discussion. There they have given the complexity of the algorithm and its maximal accuracy, which they obtained so far with the particular algorithm. Like that, they have given some comparison. So we have to choose our procedure, okay, which is less complex,
Yes,
okay,
sir.
because we are not interested in getting 100% accuracy.
Yes,
Okay,
sir.
100% accuracy is a overfitted outcome. Sometimes they may say this is an error. So
Yes, sir.
we need some acceptable accuracy with the minimal time.
Okay, sir.
So complexity also must be less. So like that, we have to choose the algorithm, not necessary to choose GoogleNet, etc., etc. Um, that is the number of parameters in that particular algorithm must be less, ma'am. Like
Okay.
AlexNet and VGG 16, not
Yes,
19.
yes.
16 also gives best result compared to 19, even though the layers are layers are very less. 16 gives good result compared to 19, ma'am.
Okay.
Yes, ma'am. Yes.
So my question was actually, if I've designed a convolutional neural network,
Yes.
and
If
if I want to find out which part or which area of the image is contributing in classification mode,
yes, yeah, yes, yes, yes.
how
Now I
can we do
understood.
that,
You want
sir?
to say you want to fetch intermediate layer result. Am I right, ma'am?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Intermediate layer result in MATLAB. I think in MATLAB, after running,
Okay.
everything will be stored in intermediate layer. Okay, we have to run some separate code to
Okay.
fetch. We have to say this line or this code from that is outcome of this layer.
Okay.
For example, say convolution one outcome. Convolution one's last layer's outcome and max full layers outcome I need. Like that, we have some separate code which is there
Yes,
that
sir.
must be executed to extract the intermediate value. Otherwise, in
Okay.
finally we'll get only confusion matrix.
Yes, sir.
Then it's only classified value only we'll get, ma'am.
Will do. Yes,
Similarly,
sir.
we implement the segmentation. Finally, we'll get either a binary image or some image whose background is in violet in color and whose extracted section is in yellow in color. Okay, the violet and yellow will be converted into black and white when we need a binary image. That is intermediate result. We have to put some other effort in order
Okay.
to extract it.
Okay. Okay, sir.
Yes, ma'am.
Thank you very much, sir.
Thank you, ma'am.
I'll try
Thank you very much.
working on it, sir. Yes,
Yes, ma'am. You can contact
sir.
if
Okay.
possible. I can help you. Thank you, ma'am.
Yes, sir. Thank you, sir. Bye.
Yes.
Sir, good afternoon.
Yes, ma'am. Good
Sir,
afternoon, ma'am.
myself Nisha. I'm
Yes,
doing
ma'am.
my research in magnetic resonance spectroscopy, sir. Sir,
Yes, ma'am.
I'm
Yes.
not getting, yeah, I'm not getting the data set
No,
for
no,
this
no.
MRS.
My question is that's why I asked it initially.
Sir.
Spectroscopy means what kind of image you expect?
Sir,
Fluorescent.
sir, it's a MRI plus a signal. MRI plus a spectrum we are getting.
Like the,
MRI images plus I'm getting a spectrum. The different chemicals present in
so
the brain.
um that image I think it will not be available for research, ma'am. You have to
Okay.
approach some particular hospital if possible. Otherwise, will it be possible to analyze some existing image into like I have sent some first day I have discussed something. We can plot some that is MRI. We can split the MRI image into various other images based on its frequency spectrum. Will it help you? No, I think it will not help you. Image
No,
which is
sir.
splitted. No, what you expect is you are expecting what the tissues or chemicals which is existing in the brain in
Yeah, sir.
image form. I'm right.
Yes, sir.
Yeah, but it will not be available for research, ma'am. In my view, I don't know this kind of images, but you can approach some dedicated hospitals. You can search and you can collect. I think nowhere I found this kind of image because currently for some work we elastogram some image we searched for breast cancer, but they provided only the image which was existing in internet. That is their website.
Yes, sir.
They refused to give the real image because they allow that kind of images, some recent one. Sometimes they may expect some MOU or some something to be executed. Otherwise, they will ask you to do some research work under their guidance or with their collaboration, like that they ask. Then if you are ready for that, then if you can execute some MOU with them, then they may provide that kind of result, man. But you have to search hospital level, not scan
Hospital.
center. Scan
Okay,
center,
sir.
in cancer center, it will not be available. You have to approach some doctor, some radiologist or some doctor who is in hospital, not
Okay,
visiting,
sir.
who is working in hospital. Like that, you can approach, ma'am.
Okay, sir.
Yes,
Okay.
thank you, ma'am.
Thank
Thank
you,
you very
sir.
much. Yes, ma'am.
Once again, thank you, sir. It was
Yes,
a
sir.
very
Thank you very much,
effective
sir.
and informative session.
Yes, sir. Yes, sir.
Our
You,
client is holding segmentation, CNN-based segmentation. All these topic were very interesting. It will help the participant in their research, sir.
thank you, sir. Thank you very much. Tonight I will.
Excuse me,
Yes,
sir.
sir.
Yes, ma'am. Yes, please.
Sir, I have a query.
Yes, ma'am.
Sir, while we are working the pre-trained convolutional neural network, so how many images, if you are getting a pre-trained network, we need to train it with the help of some images, right, ma'am?
Yes, ma'am. Yes.
Yes. So how many images we need in order to retrain the pre-trained network, sir?
It depends on your data, ma'am, because just to switch off your 1 minute, ma'am. Just you. Mic, can you switch it off, ma'am?
Yes, sir.
Yes. If we consider the pre-trained model, a data set, it's not necessary. That is a minimal data, say, for example, 100 image, 150, 200, more than sufficient, because every CNN approach is already having another one thing called data augmentation section. Okay, the in data augmentation section already it will be having some functions like rotation of image, zooming, then rotating the image, flipping, rotating with a degree, that is some angle in steps, like that. It's already there. We can also implement. For example, say I am giving only 100 image during pre-training. Say here I am having rotation with 3 different angles. So 100 image will be converted into 100 plus 400, so 500 image. So image, how much we are giving, that is secondary. What kind of data augmentation we are going to implement before the training, that is essential. Otherwise, if you want to skip the data augmentation, then you have to provide the sufficient number of images. For example, say you have to provide say 500 or 1000 images, so that the CNN learns clearly and it able to differentiate clearly between the background, normal region and abnormal section. So the number of images depends on what kind of data augmentation you are going to implement before pre-training the model based on your data, ma'am. Are you okay, ma'am? Thank you.
Okay, sir. Okay, sir. Thank you. Sir, if we are working with convolutional neural network if for a classification problem, after we are predicting our result, how can I locate the particular abnormal region? How can I include the segmentation part after the classification, sir?
Ma'am, hello. If you are implementing classification, you will not get segmentation result. So classification is different, only one section. If you want to implement segmentation, then you have to include encoder. That is the classifier is an encoder without the fully connected as well as the softmax. If you take the first section after excluding the fully connected and softmax, the remaining section is an encoder unit. Same section, once again in reverse order, it must be implemented there as decoder. Okay, if you use decoder, then only you will get segmented output. Classification task is separate, segmentation is separate, ma'am. Yes, ma'am.
Okay, sir. Thank you. Thank you so much, sir.
Thank you, ma'am. Thank you, ma'am. Yes, sir.
Thank you, sir.
Thank you very much, sir. Sir,
So we
anything
can
else, sir?
conclude.
Yes, sir.
I think no questions
Hello.
from participants. Sir.
Hello, sir.
Yes, sir.
Sir, sir, will you please tell us any tool for feature extraction and designing the CNN? Feature extraction tool.
Yeah, feature extraction tool we should not supposed to use, sir.
Yeah.
Because we have to first we have to
Yeah.
decide what kind of feature we are going to extract, either machine learning that
Yeah.
is handcrafted or CNN based. CNN based means it will do automatically.
Yeah.
Machine learning feature, if we want to do, first thing we can consider GLCM
Yeah.
feature.
Yeah. Yeah.
Then next GLDM.
Yeah.
Otherwise, who
GLR,
movements, GLRM. What
RM,
otherwise,
yeah.
my kind request.
Yeah.
A gastric polyp detection. Some website is there.
Yeah.
There, if you visit, they have listed the number of features must be considered for the images based on the grayscale as well as
GLCM
RGB
based.
scale.
Sir, actually,
Not
I want
only
to GLCM based features.
Yeah, I will give code. GLCM, it gives only 25 features. That is more than sufficient to get 90 up to 90% result. It is sufficient.
Yeah.
If you want to get more than this 90%, then you have to combine some other features along with the GLCM.
Yeah.
Yes, sir.
Yeah. Thank you, sir. One thing I would like to ask you, sir, for
Yes, sir.
designing the CNN, sir, any
Yes.
tool is there for designing the CNN? CNN
Tool
diagram.
is there. Yeah, CNN diagram, it's there, sir. Everything is in MATLAB.
Yeah.
But my request, you can use already someone has designed some CNN. It is readily available in the MATLAB web central. You can take that. First, you can explore it. After that, you can modify it according to your need.
In MATLAB, sir, no?
Yes, sir. MATLAB Central. That is the website.
Okay, sir. Okay. Thank you, sir.
Okay.
Thank you very much.
Thank you, sir. Thank you very much, sir.
Any more
Yes, sir.
questions from participant side? I think no, sir.
Yes. Thank you, sir.
Thank you,
very
sir.
much.
It was a very effective and informative session. We have covered joint thresholding, segmentation, CNN-based segmentation. All these topics were very interesting. It will help the participants in their research. Thank you very much, sir, for your time and
Yes, sir.
valuable
Thank you very
knowledge.
much, sir. Yes,
Thank
sir.
you.
Thank you very much. 1 minute, sir. Let me post my. Sir, no, yeah, I have posted. Thank you very much, everyone. Sir, thank you very much. I thank everyone for joining. I also thank Dr. Ram sir for this invitation. Thank you very much. If you need any data set or any basic code, okay, I request you to contact me or you contact Dr. Ram sir. He may provide, because today I will share the code with Dr. Ram sir. So he will provide you. Okay, I thank you everyone for this opportunity. Thank you very much. Thank you, sir. Sir, thank you very much, sir.
Thank you, sir. Thank you.
Yes, sir. Shall I log out, sir?
Yes, sir.
Yeah, thank you, sir. Thank you very much.
I request all the participants to have a lunch break. We will meet again at 3 p.m. Thank you all.